My name is Divyar Dikshit, and I am working as a lead structural engineer in one of the reputed, consultancy firms working mainly in metro domains. And I have around 12 years of working experience. I have done my master's in structural engineering from IIT Delhi. I have worked on some of the reputed metro projects like Chennai Metro, Kanpur Metro, and some packages of Delhi Metro project. Right now, I'm totally working as a lead engineer, leading a team of 15-20 engineers who are working on the elevated part of the metro viaducts. So as Roshan pointed out to each one of us, that government is focusing a lot on the metro infrastructure, mainly because it is a quick mode of transport and the cities getting congested, day by day. So metro, they are focusing much on metro, and especially elevated part of the metro is their focus area. The reason is that not only does it add beauty to the city's landscape, it also is a cheaper option as compared to the underground part of the metro. So, and it takes less time to build as compared to the underground metros, as well as less costlier. It is less costlier, and also the construction challenge can be handled relatively well if we are constructing above the ground. So in this course, we will be learning about various aspects of designing of the elevated metro structures. We will be covering the entire gamut of planning, designing, as well as the execution of metro structures, focusing on the elevated part.
Yeah.
Basically, yeah.
Thank you for such introduction, sir.
All right. So here we see this presentation will be mostly graphical. I would be mostly discussing and talking to you about the various aspects of elevated metro design. We'll try to keep it short and simple for you all to understand, and explaining to you what all we'll be covering in the course. So here we see a typical elevated metro viaduct, and we see that it passes through the city's landscape so beautifully without disturbing the existing traffic, as well as adding to the city a pollution-free mode of transport. So this is the elevated part that is being shown here, and we see here quite a few components of the elevated part. Starting from the metro itself, we see that the superstructure, the part which takes directly the load of the metro, it is a U type of a structure. So this is one of the very famous options that are being used nowadays by metro authorities, because it is a lightweight structure and it is a precast structure. Takes very less time to construct, but designing of it, since it is a precast, pre-stressed, pre-tensioned element, not many people are too familiar with the design of this kind of a structure. Also, it is an open web structure, which you'll see later during the course, how to design an open web structures and what exactly is an open web structure. Below that, we see the piers, the circular supports that are taking the load from the superstructure down to the earth. And below that, below the earth, we have the foundations, which are mainly the pile foundations. And above the metro, we see the overhead electrification cables, which these poles you can see, they provide power to the metro. And basically, there are two types of electrification systems that are used nowadays. One is the overhead electrification, which is known as OHE, and other is the third rail. So in the OHE, we have to erect these poles and we need to run these lines, electric lines, and the metro needs to derive power from that. Whereas in the third rail system, we have an additional electrified rail. We have two rails on which the metro plies. There is a third rail adjacent to it from which the metro derives the power. So that system is also being used. It is of course a costlier system as compared to the OHE system, but then it brings a better look to the metro and we do not need to provide all these poles for the electrification and all. I would like to discuss with you the state-of-the-art technologies that are being used in the metro construction and design. What we see here is a typical metro pillar on which we have a launching gantry, which we see in blue color. The structural elements, which are these box type elements, which are being erected onto these piers. So we see here that these are precast elements. We don't need to stop the traffic which is plying below this metro which is being constructed. The traffic keeps moving while this construction keeps on taking place. And these precast elements are factory made, and they are match casted on the side. By match casting, I mean they are joined end to end, and then they are stressed steel cable that runs to these elements and then ties them all together. As I said, construction no doubt is challenging, but we have the machinery and the equipment and the know-how to safely execute this construction. And also, it does not affect the existing traffic, existing road which is going below this these piers. So metro construction can go on without interrupting the traffic that is flying below. Now you see, in the course we will be understanding how to design this kind of a structure, because we see you see, when we design a structure, we need to take into account the loadings on the structure during all stages of its life. By its life, I mean from the day it is casted to the day the bridge goes out of service, which is about 100 years of time. So during these 100 years, it will be exposed to various kinds of loadings, wind loadings, seismic loadings, metro flying on it regularly, as well as the loadings during the construction. So during the construction, you see, we have very small elements. Typically, the element lengths about 3 meters maximum, and they are being joined together. So at this point of time, also many loads will be acting on these elements, and they need to be structurally stable. They need to remain intact before they are put in place. So in our structural modeling that we do in the softwares, I'll discuss which softwares to do that modeling. We need to simulate this stage also. We need to simulate each and every stage of loading that is there on the structure, and we need to model all these things into our model to get the exact forces, stresses that come on the structure during the launching operation. The launching is being done here. Yeah, in the state of the art part, we see here a typical metro station that is there, and you see the structure that is taking the load of the metro is, it is right now the metro is empty, nobody is there on the station. It has got, it has got a good look, good feel, steel roofs are there, everything is there. And you see, as soon as the metro enters the station, we have, a lot of people who want to get into the metro, and, adding a lot of load to the beams and the columns of this station. What I mean to say is, as a structural engineer, as a person who has designed this elevated metro structure, we need to be aware that what are the limits within which this structure has to work. So the beams and the columns, the ones that I showed you in the first slide, they have to take all of these loads, and they are all pre-stress elements. So in pre-stressing, we need to know what is the minimum load and what is the maximum load that is coming on the structure. If we put a load which is lesser than the minimum load, then also there is a possibility of developing of cracks in the structure. And you see here, such a huge load that comes on the structure, we need to design for these loadings. There is a metro, and then there is such a huge crowd. And on top of that, since it is a moving train, once it moves, there are dynamic effects which are induced. So all of you are here are engineering graduates, and some would be practicing engineers also. We know that the dynamic effects on the structures could be as high as the static effects. So we need to consider all those effects into our design to ensure the safety of the structure for 100 years or so. So what I mean to say is, as a structural design engineer who's working on the elevated metro project, we need to take into account a lot of factors that we have to be 100% sure that structure is safe, reliable, and also on the other side, we have to make it economical, because India is not a very rich country. We cannot spend money extravagantly on the construction of metros and everything. So we have a limited budget which is being given to us by the client. The client also has a limited budget which is given to them by the government, and they have to finish the project within that budget. So we have to ensure that we provide the most economical solutions while not compromising, at the same time, not compromising on the safety of the structure. So it is important for a structural engineer not only to design a safe structure, taking all of these loads into account, but to provide to the client the most economical option. And that is where the role of a seasoned structural engineer, of a person who has known his trade and who also understands the economics of it, can become successful. So in this course, we will talk about the structural aspects as well as the most economical options for metro providers. For example, how much span should we provide? What kind of structure should we go go ahead with in various kind of situations. So that comes under the planning part of it. That planning part, you will normally, an engineer is normally exposed to the planning part gradually. And, after 4 or 5 years of continuous experience, he gets to understand what all things goes into planning of a metro viaduct, elevated viaduct. But in this course, I'll try to explain to you all those fine aspects, minor aspects that help us design and a structure, economical structure, as well as a structure which is robust enough to take the loads. Leading software solution providers, typically the software that we are using in our design offices these days for elevated metro viaducts is MIDAS Civil. It is a very widely used software, and it has the ability to do time-dependent modeling of the structure. For example, some of you might be familiar with Staad, and Staad also is one of the software that we use extensively. But in Staad, the issue is that we cannot do a time-dependent model. For example, we cannot model a structure from day 0 to 100 years of its lifetime. We can model the structure at a particular point of time, for example, after 10 years or during the start of the metro. But we do not have that option of inputting the time as a variable in that. So creep effects, time dependent effects like creep and shrinkage, we cannot provide in Staad directly. Whereas in MIDAS, we have that option. Also, MIDAS has a very good, GUI, graphical user interface, for designing of pre-stressed structures. So we use extensively MIDAS Civil software, which will also be exposing you to that design aspects on MIDAS Civil during this course. Then we have a robot structural analysis professional, which is a software by Autodesk, and we have Staad Pro, which you all must be aware of, which is being used by most of the structural engineers in buildings, also building design, as well as highway designs, highway bridge designs, and all. And then we have SAP 2000. SAP also has the ability to do a time-dependent modeling. So we can use either MIDAS or SAP, but MIDAS is more extensively used because MIDAS has worked more on developing the bridge-relevant aspects of its software. So we have many ready-made commands, very fine GUI, and we have a lot of help options which are available. For example, if as a structural engineer we are stuck somewhere, we can quickly refer to those help options and find out the solutions that we come across to the problems during the modeling of the structure. So in this course, we'll be working on MIDAS Civil, Staad Pro, as well as we also have a software which is known as ST1, which is a French software. We might be requiring that. We'll see how we will manage that. We might be requiring that software, but whatever softwares will be required, we'll be providing you those softwares. All right, so let's go a bit into more of a technical details of metro viaducts. Of course, we'll be exploring them in its entirety during this course. What all we'll be covering typically in the course will be the various kind of structures that we use in metro viaducts. For example, here you see a long span bridge. It has been built by a balanced cantilever technology, which is a relatively new technology. It helps us construct long span bridges, typically in the range of 60, 70, 80, 90, meters. And it also helps us to, span larger spans without disturbing the traffic below. So you see here that we have rails which are, it is basically a span which is going below the rail, above the rail, and rail operations cannot be stopped. So since we cannot stop the rail operations, we have to find a technique that we can build a bridge across this railway without stopping these rail operations. So that means we cannot take a formwork from the ground up to this level and then construct this superstructure at our leisure by stopping the railway. We don't have that option. On the other hand, it is also a large span which has a lot of load. So we need to ensure that during its construction, the railways which are rails which are plying below, they remain safe and construction is done safely. So for that, we have a balanced cantilever technique, which is the state-of-the-art technique. And balanced cantilever bridges are typically long span bridges. Not many people have the requisite knowledge to design and construct these type of bridges. Of course, we have got specialists who are working in this field, and these type of structures are now routinely deployed for long span crossings. For example, we have long wide rivers or such wide railway crossings that we need to span across. So in those situations, we typically use this kind of a construction technique. So This is a state-of-the-art technique which is nowadays deployed, and we can easily span up to 150 meters by this technique. So that is one thing. And we, as practicing structural engineers, we need to learn about these new bridges because these will be more frequently used in future. So we need to understand how to design these, how to design them, and of course there are various aspects which we need to learn and understand. So as I pointed out, in the metro we have three main components. The first one is the elevated component. The second is the underground metros. We all must have traveled through metro, and we are familiar with this. And the third is the stations. So typically stations are arranged at approximately 1 kilometer apart. I'm talking about stations which are there in Indian metro cities like Delhi and Chennai. So we have the elevated portion, we have the underground portion, and we have the stations. Right now, the elevated portions has also been developed in a way to support traffic at two levels, which you see in this photograph, that we have a metro which is plying on the top level, and then we have a highway which is going below that. And this metro and this highway, they are being supported by the same pier, and the same foundation. So as structural engineers nowadays, these type of structures are being used regularly. We need to be able to design this structure, this pier, the superstructure, as well as this highway bridge for metro and the combined effects of metro and highway loads. So we have two different codes. For metro, metro designing, we use IRS, which is the Indian Railway standards. For highway bridges design, we use the IRC, which is the IRC 112, which is the code for structural design of Indian highway structures. So we need to have knowledge of both these codes. Also, since the metro is running on that, we need to take into account the rail structure interaction, that is the dynamic effects of rail moving onto the structure, as well as the dynamic effects of the vehicles which are plying on the highway part, level 1 of the bridge. That needs to be taken into account. So elevated part, so you see this is quite challenging. I mean, building a two-tier bridge is, construction of course is challenging, and the design also is a challenging part because we need to take into account so many aspects, a few of those which I highlighted just now to you. But even then, this elevated part helps solve a lot of commuting problems for people who are using it. It decongests the roads, and therefore it is a choice of the metro authorities. They want to build these kind of structures, and that is why there is a need for engineers who can design these structures, who can construct them. And therefore, this elevated part of viaducts becomes an important area wherein, if we learn the various aspects of its design and construction, we'll be able to not only secure good jobs, but also this will be there for the future. And we can always take pride in designing these structures. Whenever we pass across them, we always see that these kind of structures that we had designed or constructed are being used, and they are helping ease the life of people around us. Also, as I pointed out earlier to you, that elevated part is less costly as compared to the underground. So it is more preferable to go with elevated part. And that is why in the priority sections of most of the metro corridors, by priority section, I mean the section which is built first of all, they would focus on the building of the elevated part of the metro. For example, in Chennai, they first constructed the elevated part and then they went to the underground. In Lucknow Metro also, those of you who know, the priority stitch was all elevated, and then they went to the underground, and so on and so forth. And then, of course, the other part of the elevated structures is the stations, which again is a challenging design job as well as a construction job, because that station has to incorporate a lot of stuff. For example, the ticketing counter, the electrical components of the metro, and as well as they have to host the traffic and all the services which are required for safely running the metro. So all of them are required. And as a designer, we need to take into account not only the ease of the people who use the stations, but also we need to design them in a way that the services run smoothly. So the elevated part of the metro consists of elevated metro viaduct as well as the elevated stations. Then also we have underground stations also. Right? So these are the main components of the metro viaduct that an engineer of metro structure, that an engineer who wants to work on them would want to learn. But then there are subcategories. For example, if you go to a design firm, you will have a different team for the design of elevated viaduct part. You'll have a different team who would be working on the elevated stations, and you'll have a different team who will be working on the underground part of the tunnel part of the metro. Because they require specialized knowledge, they need to be dealt with separately with separate set of codes, and therefore we have these are three specialized areas. So we can choose to go in any one of these, and all of them are equally rewarding for a structural engineer. But then it also depends on our interest where we want. All right, so here we see a good view of the elevated with the underground metro, and then we have an elevated station, and you see that the viaduct is being integrated into the station. So we have a pier which you see in the middle of the station. On the pier we have a pier cap, the rectangular type of a frustum type of a structure that you see. This is known as a pier cap. And then we have the cross arms, the cantilevers that you see there, and on top of that we have the beams which are placed on that the superstructure on which the metro plies. And then this metro station itself is a beam column arrangement. You see on the darker part of your below the station, you would probably be seeing a few beams which are running. So we have the beams, and the station engineer who has designed these stations, he has the responsibility to design all of these beams, the columns, as well as the entry which you see on the left side. We have a walkway wherein we have an entry, and the passenger enters from there. So that walkway also needs to be integrated into the station. So you see, a station has to integrate a lot of stuff into it. The walkway, the people coming into it, the metro train which is coming into the station and which halts at the station. So its signaling aspects have to be taken care of. The ticketing aspect of the commuters has to be taken care of. So metro building in itself is a challenging design. Itself is a design challenge, so which we need to address, and it is an interesting part. And people who have the knowledge of designing of these metro buildings, they are in good demand in the job market. All right, so coming back to the elevated part of the viaduct, which we started our discussion with, you see here a schematic diagram of typical structural arrangement that we follow in the metro viaducts. So going from top to bottom, we see there are railings, and then we have a girder, which is known as a superstructure. So superstructure is basically the part which hosts or on which the metro train actually runs, which takes the load of the metro directly. So there are rails which are fixed on this superstructure, on this girder, and on those rails the metro plies. Then this girder is placed on bearings. You see on the third pier we have bearing which are being put in the shown in the yellow color. These bearings are put on pier caps. The rectangular orange element which you see below this is the pier cap, and this pier cap is kept on the pier which you see on the middle pier. You see left hand side we have marked it as a pier, and this pier cap and pier and the pile cap which is below this pier. So this pile cap is a structural element which typically takes that load of the metro as well as the self weight of the girder, the pier and the pier cap, and it transfers them to the foundation. Foundation here we see is a deep foundation, which is a pile foundation. Normally we go with pile foundations in metro viaducts because pile foundations are typically deployed where we have the need for where we do not have a good strata at the top, and we need to go deeper into the soil to find a proper bearing. This is the typical schematic or the typical layout of a metro viaduct. But we also go with open foundations where we have a rocky strata, but normally that is not very frequent. So most frequently this would be a typical structural arrangement that we find in a metro viaduct. So we, as a design engineer who's working on elevated metro part, we need to be familiar with designing of all of these parts. Now in this schematic, in this particular diagram, it looks these are only 4 or 5 components that an engineer needs to design. But these 5 components in itself, require a lot of expertise, a lot of expert knowledge to understand what type of, how to design it first of all, and then what type of structure to employ. For example, in girder, we have various options. We have a U girder which can be used. We have a box girder. Then in box girder also we have the option of going with the precast part or the cast in situ part, pre-stressed part or reinforced part. Whether to make it pre-stressed or to make it reinforced. Then again, we need to decide whether we need to go with open web structure like a U girder or a box girder or an I girder. So, or a steel girder, or we need to adopt a balanced cantilever construction using a box girder. So there are a lot of combinations, configurations that we need to take into account, which suit our requirements as well as the contractor's feasibility to construct. For example, as a designer, if you propose a box girder, which is, being constructed by cantilever construction method, and the contractor is not able to do that construction, then that exercise will be futile. We'll have to go with the other option. So it not only depends on the comfort of the contractor, it also depends on the existing conditions that are there, on basis of which we choose the type of the girder. And then all of these types, as a designer, we need to know the design of all of these types, the ones that I listed. Because when you are a practicing engineer, the contractor or the client would ask you for the best possible options, and they may also ask you for 2 or 3 options wherein they can pick and select which ones they want to go with. Similarly, with the bearings, we have the options of elastomeric bearing or the pod PTFE bearing, and then there are a few advancements in the bearing right now. Going forward, for example, we have lead rubber bearings which behave very well in the during the seismic events. So we need to decide which of the bearing arrangement we want to go with. Then in the pier cap part, we have to see whether we want to go with the RCC pier cap or a pre-stress pier cap. In metro viaducts, typically we are going ahead with pre-stress pier caps because they are precast, they are launched onto the piers, and then they are pre-stressed. So the construction becomes quick, as well as they are very slender. They look very, they blend aesthetically into the landscape of the city. For those of you who would have seen the airport line of the Delhi Metro, they must be aware of this, these slender pier caps, and they look very beautiful, and they add to the aesthetics of the city. So again, here we have the option of going with the RCC pier cap or the pre-stress pier cap, but the pre-stressing, of course, has its own challenges. So that thing comes at a cost. Then in the pier part, we need to decide what type of a shape of a pier we want to go ahead with, whether it will be a circular pier or rectangular pier, or a rectangular pier with semicircular ends and all those things. So there also we need to be familiar with what are the options we can present, what are the options we can go ahead with, and then those options can be presented to the client and then they can decide. Pile cap is relatively a standard type of a structure. We go with normally with rectangular pile caps, which take the load from the superstructure, the superstructure and the substructure, and transfer to the piles. But normally what happens in these pile caps also, there are quite a few challenges that we face during the construction. When the contractor actually goes on to do the piling, many a times they encounter various utilities. For example, the underground cables which are running through, and they might also encounter other utilities, the pipelines, and all those things. So, and then they come up with the problem that they cannot do the piling at that particular location, the location that the consultant or the designer has provided to them. So then as a designer, you need to come up with alternate piling locations, alternate pile configurations, and which would necessitate or require you to design a non-standard pile cap. It could be a pentagon type of a pile cap or a hexagon type of a pile cap. It could be a different shape altogether. So all those are the challenges which we come across during the construction of the pile and pile cap, the foundation part. And then of course there is pile. Typically these piles would be 20 to 30, 35, 40 meters into the ground. So they have to be bored into the ground, and many a times the contractor would come up and would say that there are concreting issues, there are honeycombing issues, what to do now, and the pile does not pass the pile load test. So there are so many challenges that as a designer you need to face during the construction also. It's not that we have just designed a structure and then we have issued the drawings to the office, the client's the client and the contractor's office, and then we are free. So as a designer, we need to be involved in every aspect of construction also, and we need to come up with solutions, quick solutions that the contractor might face during the construction. So all in all, as a person, as a structural engineer who is practicing in the elevated design of elevated metro structures, we need to be aware of not only the structural aspects of the things, but also the various construction issues that come up, the various structural options that are required that we can present to the client, as well as the various state-of-the-art technologies that are being deployed in other countries, so that we can follow them in India or wherever we are practicing.